Whoa, does that ever happen where it actually works the right way? It's amazing. Okay. So I recommend just using the up and down buttons. Okay. I had a clicker, but the batteries.
Oh, the batteries.
There you go. Thanks. So.
Well, thanks. Oh, Lisa's got the clicker.
Oh.
Maybe I should.
Oh, yeah. Oh, all right. Thanks.
All right. Well, thanks for having us here today to talk about our research on formation of surface foam in the Finger Lakes. Rick's here with me. He's the other half of Global Aquatic Research. And I just want to acknowledge some of our collaborators, Doctors Ryan Pereira and Philippa Ricard. They're at Heriot-Watt University and Edinburgh, Scotland at the Lyle Center. The Canandaigua Lake Watershed Association, which really got us started on doing the research on the foam. And Robbie Sullivan and Dr. Nandini Carr, who are at SUNY Brockport. Robbie helped me for his senior research thesis a couple of years ago, so he contributed to this as well. So in 2019, we got an email from Lindsay McMillan at Canandaigua Lake Watershed Association, and she sent us this picture, and she just wanted to know what is this? And so that's what got us interested. We looked at this foam and said, well, we're both aquatic chemists. Let's see if we can figure out what the heck this stuff is. If you think about how foam forms in lakes, materials go into the lake. They're contributed by terrestrial or land-based sources through the watershed. You have plants, soils, bedrock, pollution washing into your lake. And you also have sources of organic matter being contributed from aquatic things like phytoplankton, the mussels in the lake, seaweeds, bacteria, and also organic matter released from the sediments. These things dissolve into the lake water, and if they're less soluble in the water, they'll accumulate in the very uppermost millimeter of the water, and that's what we call the surface microlayer. And a lot of times these compounds will reduce the surface tension of the water, and when they do that, that allows air from currents and wind and other things to be entrained. And if the materials make that surface tension really low, you can form really stable foam. And so that's how you get foam in general on the lakes. In practice, this is sort of what it looks like on Canandaigua Lake when they get these big foam events. So it starts out with wind-driven circulation, Langmuir cells, making these streaks of foam. They converge. The wind pushes them around, and eventually the streaks will blow on shore. And if the foam's really stable, it can persist there and keep piling up, and it'll last for days sometimes. So in thinking about how we were going to figure out where this foam was coming from, we decided to do a bunch of chemical analyses, and we went out, we took foam and lake water samples. And we also sampled some end members. So we went and got materials from the stream. We did a plankton tow, we collected quagga mussels, and we collected a bunch of different kinds of seaweeds. And we considered those our end members. And this is just an example of some of the chemical data that we generated. This is what's known as a source plot. So you have carbon and carbon nitrogen ratios on one axis, carbon isotopes on the other. And this was us trying to fingerprint that foam and see what the source is. But you can see from this plot, the foam's in the yellow there, and it's really not plotting with any of our end members. So what we realized is the foam, we can't just trace back to one single source. It must be concentrating something that's a certain molecular type. And so in thinking about what those molecular type might be, we started with kind of the three main biomolecules that are made. Those are lipids or fats, carbohydrates, which are sugars, or proteins, which are made of amino acids. We did some chemistry on that, and we immediately kind of ruled out the proteins. We knew it couldn't be proteins because our foam had a lot of carbon in it, and proteins are really rich in nitrogen. So there was nitrogen there, but there was a lot more carbon. So we ruled out proteins. We looked at the lipids, but when we did lipid extractions of the foam, we found a really low number of lipids, but they did give us some really good information. They allowed us to say, it's not a terrestrial source that's providing the material in this foam. It's something coming from within the lake. And so we were left with carbohydrates, and we looked at the carbohydrates and figured out what kind of carbohydrates were in there. And there was a lot of polysaccharides, which are chains of sugars together. And when we compared kind of the structure of the polysaccharides with our in-lake end members, they looked a lot like plankton, the plankton toad that we looked at. So we thought, well, what could be putting all these polysaccharides in the lake? Where could these be coming from? And in Canandaigua Lake, at least, when they have harmful algal blooms, it's mostly microcystis. And microcystis, when they bloom, surround their cells in a really thick layer of what's called extracellular polymeric substances. So in the image there, you see all the little dots. That's a microcystis colony. All the dots are individual cells. And that clear stuff surrounding them is their EPS, or their exopolymeric substances. And that's what allows them to regulate their environment, allows them to outcompete things. When they bloom, they produce a lot of this stuff, and it's very polysaccharide rich. We think those polysaccharides are dissolving into the water, because when we look at the literature, a lot of lakes in the summertime, up to like 25% of their organic carbon pool can be contributed from these type of substances, from these exopolysaccharides. So that made us think, maybe there's some connection with these harmful algal blooms and the polysaccharides they're producing in the HAPs. So we wanted to see if we could kind of make a better connection between the chemistry of the lake water and the physics, that the physical processes forming the foam. We went back out in 2022, and this is a picture of a huge area of foam. This is the southern end of Canandaigua Lake. Huge area of foam. That's our sampling device right there. We've come up with a pretty good way to separate the foam from the water and skim it off. And we took a bunch more samples of lake water and foam. And we also happened to be able to get a sample from Skinny Atlas Lake. So we started realizing, like, a lot of the lakes around here are getting these big foaming events sometimes. And we sent the samples off to our colleagues in Scotland because they have a really advanced piece of analytical equipment. It's called liquid chromatography, organic carbon detection, organic nitrogen detection. And what this allows us to do is to take a whole water sample and look at the organic matter in it and characterize it all at once without having to extract it. It gives you a big snapshot of the carbon and the nitrogen in the organic matter pool. And on the left here, you'll see two of the chromatograms. So this is kind of the output from the analysis. On the top is water, and on the bottom is foam. You'll note the scales are different, but also where the major peaks are really different. And I just plotted all the samples that we took with their different organic matter fractions in terms of percent carbon there. And you can see the foam samples all look very, very similar, even Skinny Atlas and Canandaigua. The lake water samples look very similar, but the foam and the lake water are really different. The lake water's got a lot of humic substances, and the foam has a lot of biopolymers. So by measuring all these things, we can kind of look at enrichment factors. So that's just the amount of one constituent in the foam divided by the amount of that same constituent found in water. And what we found was the foam is really, really enriched in organic carbon. That wasn't too surprising. We found a lot of carbon in our other measurements, but it's got something like 15 times on average more organic carbon in it than the lake water itself. And a lot of that organic carbon is in the form of biopolymers, main constituent of the foam. There's about 50 times more biopolymers in the foam than in the lake water. So lots of organic carbon. Well, how can this contribute to what we're seeing in terms of foaming? So we did a physical measurement for how likely the water is to foam. That's called surfactant activity. And what you can see here is this is just total dissolved organic carbon in the foam and the water plotted against surfactant activity. And we found a really excellent relationship between the amount of organic carbon in the foam and its surfactant activity. So that made us think, well, these things are highly correlated. They must be related somehow. And then we separated out the biopolymer organic carbon, and biopolymer organic carbon would be the polysaccharides. Chains of sugars, they're a polymer. So biopolymer, carbon, polysaccharides, again, we got a pretty good relationship with surfactant activity there. But not all biopolymers are polysaccharides. Some biopolymers are proteins. And when we looked at the proteins with the surfactant activity, we actually got the opposite relationship. We got a negative relationship. So proteins, as they decrease, then your surfactant activity goes up. And that made us start thinking about it as well. Proteins, polysaccharides, they're both biopolymers, but what's the big difference? Well, proteins have nitrogen in them, and nitrogen can be a really good food source for things. So we started thinking, well, maybe these proteins are somehow being degraded in the foam. And we looked a little deeper into our nitrogen data, and that's what we found on the top there. As you can see, as the protein content in the foam goes down, the amount of ammonium in there goes way up, and those are really high ammonium numbers. This is an oxic lake. Ammonia is the reduced form. We wouldn't necessarily expect to see that, but there's a lot of ammonium in there, and ammonium is really important because it's the most bioavailable form of nitrogen. So not only are maybe these HABs producing a bunch of polysaccharides, they generate the foam, but then on top of that, the foam can actually act as a nutrient recycler, make a lot of nitrogen available and maybe move it around the surface of the lake. And that could potentially be feeding the next bloom. And also the nitrogen has been linked to toxicity production. So not only could the foam be feeding the next bloom, but also be making it more toxic. So we have all these chemical measurements, but how do these kind of square up with what we've observed out on the lake? And we're really fortunate. We have a lot of citizen scientists at Canandaigua Lake who since 2019 have been using an online reporting tool. And so we've gotten hundreds of reports and photos of what the foam looks like. And one thing that we started observing were these big smooth patches in the lake. These are called surface slicks, where the surface tension of the water is slightly different from the surrounding water. And what we noticed is when we go out to these surface slicks in the summertime, a lot of times there's a HAB either forming or a bloom terminating beneath them. And the other thing we'll see on these surface slicks, this is a really, really calm day, but we would go out and observe foam on them without the wind acting to stir it up, just this foam, and it often has this really strange ring pattern. And then just beneath it, we would see a harmful algal bloom. If we think about when most of our observations from our eyes on the lake made their foam reports, it's mostly in the late summer and the fall. And that actually corresponds really well with the timing of when cyanobacteria and green algae are dominant in these lake systems. So the timing also seemed to match up pretty well. But one thing that microcystis does is make these toxins, right? So one of the big concerns about it is, were these toxins from the algae, from the harmful algal blooms, getting into the foam? So we measured microcystins, which is a toxin that microcystis algae and other cyanobacteria produce. And we measured that in lake water, and we also measured that in the foam. And what you can see here is, yeah, the foam is picking up microcystins toxin, and it does tend to be higher than the water, but not really in any predictable pattern or way. And most of the microcystins toxin that we found in the foam was actually still bound up in intact cells. So what happens is this foam forms, it gets blown around the lake, and it just picks up whatever it moves over. So you might have a lot of cells being picked up if it moves over a bloom, or you might not. And that's really what we think is determining the amount of microcystins toxin that we see in there. And that really makes sense because microcystins is really water soluble. So if it's not trapped in those intact cells, then it will just dissolve back into the water. So this made sense. But there are other toxins that are not as water soluble. And we thought, well, maybe those are being concentrated. There's a lot of literature saying that certain toxins can really, and pollutants can really be accumulated in foam. So in 2023, we went out and we collected a few more foam samples and a lake water sample, and we analyzed it for PFAS. These are per and polyfluoroalkyl substances. They're man-made substances. There are thousands of them. And they're what's known as a pollutant of emerging concern. They call them forever chemicals because they don't break down in the environment. They can have some adverse health effects, so a handful of them are now being regulated in our drinking water by the EPA and the DEC. And what you can see is these things also are known to like the air-water interface, so they are really being concentrated in the foam relative to the lake water. On the top, those are total concentrations. We found about 380 parts per billion in the foam and only about 5 parts per billion in the lake water. And that equates to an enrichment factor of about 70 times. So the foam is really picking these things up and concentrating them. And the other thing you'll notice is even though we have 3 very different foam samples, the types of PFAS compounds that are being concentrated in there are really quite similar, showing that certain compounds have more of an affinity for moving into the foam. And in the red boxes there, you'll see PFOS. This is one of the compounds that is regulated in our drinking water. And we found none of it in the lake water at all, no detection of it at all. But we found really, really high levels in the foam. And so this is really something that we think we should keep in mind because this stuff does blow on shore where it might come in contact with wildlife or people. And so it's just another pathway that people could be exposed to these type of toxins. So that was just an overview of sort of what we did. We're still working on this stuff, but we've pretty much found that there seems to be a link between foam in these lakes and polysaccharide production from harmful algal blooms. Foam might be really important in nutrient cycling. It might be a new way to think about that. And it could actually be making nitrogen available to feed more blooms or to create more toxicity in our blooms if we have it. And also foam does have the potential to concentrate some toxins at much higher levels than the surrounding lake water. So we've been continuing this research. We're working on a WRI grant this fall. We have a PFAS project and we're going to be measuring PFAS and foam on Skinny Atlas, Owasco, Seneca, and Tuca Lake. But also as part of that grant, we were able to expand our foam reporting tool. So if you see foam on the lake, we have a reporting tool for it. We're trying to collect information about all 11 Finger Lakes now, and that tool is rolled out. I can give you you can go to our website, or I can go back to the other slide, and you can get a link to that. We're also trying to come up with ways that we can predict when foaming might occur, maybe linking some of our observations out in the lake with remote sensing and satellite data, and also thinking about whether or not there's enough of this foam or it's worthwhile, it's right there on the surface, to skim it off if we can clean it or remediate it, whether that's an additional way we can help clean our water up. And finally, we just want to collect more mechanistic data on the Finger Lakes in general. Almost everything I showed you is from Canandaigua Lake, but since we've been doing this, we found that a lot of the other lakes, we've been sent pictures, get foam on them, and we'd really like to compare and see how similar they are. Canandaigua, or one Skinny Atlas sample, looks pretty similar to Canandaigua, but every lake's different here, and I suspect that maybe we can find common threads, and those are the important things to focus on. And then we also might see how these systems are a little bit different. So thanks, and I'd be happy to answer any of your questions.
So take a couple questions. Oh, I'm sorry.
No, go ahead.
As far as the long-term prevention or reduction of foam, strategy is the same as a lot of the other things that we're doing in terms of reducing phosphorus and nitrogen loading in the lakes.
Well, there really seems to be a pretty clear link between algal biomass and foam production. So yeah, if you can reduce your nutrient inputs, you're going to have less algal biomass. So I would say, yeah, that's a good place to start. And Rick just told me I should correct myself. The PFAS are in parts per trillion, not parts per billion. So don't have a heart attack, because if they were parts per billion, we should be worried. Parts per trillion. Our lakes are, at least the ones we've looked at for PFAS right now, are still relatively clean. Certainly there's polluted lakes in Wisconsin and other places where they've done these studies, and the levels in the foam are much, much higher, so.
Are you seeing any instances where you're not seeing the harmful algal blooms and foam together? Or do you have any foam that's just floating on its own?
Oh, yeah, absolutely, so, that ring shape pattern. This ring shape pattern, that's when we typically, if we start going out and it's a nice calm day and we see foam around and we see these rings, then we look closely because that's most typically associated with the harmful algal blooms. Otherwise, these polysaccharides are released in the water. They're not a real great food source, so they kind of just sit up in the surface microlayer. So you can see from that, people observed foam in the middle of winter when the lake had open water. So if there's wind blowing across and these compounds have been released or in the water at high enough concentration, you'll see foam then also.
How do they degrade?
How do polysaccharides degrade? That's a good question.
It's a chemical reaction called hydrolysis, basically. And they're very relatively. They can be easy to degrade on their own. It's like a beta O4 glycosidic bond that a lot of bacteria make the enzyme to break them down, but. But we think they have different effects just from them being in kind of a mucus, and these chains of polysaccharides start to link together. So we don't think they're as degradable as they would be if, say, you dissolve a small amount of water.
UV is not the thing.
But they will break down due to all those factors for sure. UV and bacteria, it's just, there's definitely a lag from when they get produced to when they break down. And I think because they're getting produced in the late fall, once winter hits and bacterial activity really goes down and UV really goes down, I think that's why they can persist in the next year.
Why Skinny and Canandaigua Lakes chosen for the study?
Well, Canandaigua Lake Watershed Association hired us, so that's the quick answer for Canandaigua. Skinny Atlas, we heard that there was foam there and in Cuca Lake. And Skinny Atlas and Canandaigua Lakes are very similar shape and have very similar Skinny Atlas is oligotrophic, Canandaigua's meso, so they have really low nutrient concentrations. And we just happened to be in Skinny Atlas and we were doing this sampling and we thought, well, we'll look out there, and there was foam, so we had our stuff and we went and took a sample. So that's really why. I have been sent a picture from years ago, actually, on Cayuga Lake, from Gration at CSI that someone had passed on to her. And it looks like this lake used to get huge amounts of foam forming in it also. I haven't seen any recent pictures, but I'm hoping with a foam reporting tool, we'll start to be able to track them.
But Billy, you just said that you see foam along here, right?
Yes, I've seen from.
Big swaths like in the pictures.
No.
Or I've seen a little bit, I guess, on the even down here in the state park on the shorefront, and it's pretty normal. Since I played with the foam a lot now, the stuff I saw on the shorefront here tended to have larger bubbles, and my guess is it wasn't quite as stable. It had a little bit of a different appearance, but it wasn't huge, patches of foam covering or piled up in big thick layers.
So if we were to see it on the way, we need pictures of that, things like that.
Absolutely. If you go, this is our website, it's a little bit cut off there, or if you take a picture of this with your phone or whatever, or even probably you should Google it. You can go to this foam reporting tool. It's a survey 1, 2, 3 type thing. And you just answer a few questions and describe what you're seeing in its extent, and you can upload a picture right there, and that will come directly to us immediately. So as we're continuing to do this year, we're not doing Cayuga Lake as part of this PFAS project, but in the future, we're hoping to get to all of the lakes. And so the more information we can have, the better. And it also, the foam forms, it's there. It might not be there 2 days from now. So it really helps us in response time, because we've had days where we're like, we need to go get samples and we go out and there just isn't foam that day. And then you're just out there and it's nice, but. So it's really helpful, and then it would really be helpful, I think, to compare, frequency and when people are seeing these things across all of the Finger Lakes in the whole region.
Okay, I'll do one more thing. Okay. Sometimes see foam, but it's when. Over it's not beginning to look like, a stream is coming in, like. Spring that is happening, so why that's happening, and when the foam dissipates, it's also like, but that's it.
Well, the PFAS are still there somewhere, because they're not going away.
they just
So,
got out there.
They've,
Yeah.
right, so what happens is the foam breaks down, rain is really effective at popping the bubbles. Just time, because as the foam sits, the water drains around those air bubbles and eventually they'll pop, so it will collapse back into the lake. So the PFAS just end up back probably in the surface microlayer. That's part of the research we're doing, is we're actually taking water surface microlayer. We have a sampler that can just kiss the top of the water and pull that top layer off. We're gonna look at that, and then we're also gonna look at foam. So I think it partitions out preferentially into the foam phase, but my guess is that most of those things are sitting in the surface microlayer. And then in terms of your culvert or stream coming in, well, there's really two things. So foam, if you go to a waterfall, a lot of times there's foam at the base of it. That's because of that agitation and because there's organic material there. That's lowering the surface tension of the water. So it could be that a culvert or a stream are bringing more organic materials in that are lowering the surface tension in that area. Or if the surface of the lake or the lake water there already has a lot of organic matter that lowers the surface tension. It could just be the action that, agitation and action that's getting air entrained and making the bubbles.
Great, thanks. Oh, go ahead. So from a policy perspective. Living there. So I'll make sure I have this. So foam. Two reasons. One, cycles nitrogen is one and supports that. Right? And then two, we can think about PFAS.
Yeah, PFAS are the only air water interface chemical we looked at. My guess is if there's other chemicals in there that really prefer that air water interface, we're gonna see those in the foam also. One thing we haven't done that I was trained as a trace metal geochemist, so one thing I really want to look at is heavy metals in there. Foams, if there's heavy metals, and a lot of them are buried fortunately in the sediments, but now we have this muscle issue where they're kind of reworking the sediments. So if that's getting up into the surface microlayer, I would expect to see those heavy metals being concentrated in the foam. That's been well documented in the literature. We have not looked at that either. Someone just asked me that, the other day. And there's a woman at RIT that I met, actually at FLI, and I gave a talk at FLI this winter. And we kind of discussed that, but I really need to reach out. She measures microplastics, so I really need to reach out to her. My guess is microplastics will be concentrated in the foam, because if you look at the foam, it picks up everything. It's full of bugs and plant material and just anything it moves over.
We can have more discussion, we'll hold that, we'll get Lisa and Isaac up here, but after their presentation, we can have more discussion. The presenters, thanks so much, Bella.
Over there, I thought that's fine with me.
I gotta make sure I don't stand in front of a projector because I'm like.
Don't do that, don't do that. Yes,
Good, looks good to me.
all right, great, turn it over to Isaac. Actually,
Everybody's gonna move over there now.
no,
Oh,
no,
she's
no,
gonna-
no,
all right.
come back.
All right. Oh, I use this thing. Okay. Thanks, everybody, for coming. So I guess I'll start off with just a little bit of background and some of the objectives of this project. So for a number of years, we've heard, I'm sure many of you have heard, that the canal, the Seneca Cuyahoga Canal flows into the northern end of the lake. Of course, some state agencies dispute that, and we have various different watershed maps, right? The network in CWIO have one that includes the canal as part of the Cuyahoga Lake watershed, but any state maps say no, just the Cuyahoga Lake watershed. So we decided, I came to Lisa and said, hey, can we look at this? And we brought in some other folks, but basically we wanted to do two things. One, assess the flow pattern to see where is that water actually flowing? Is it going straight out the Seneca River, or is it coming into the northern end of the lake? And also assess the water quality side of things too. So you see, we have 5 sites that we've been sampling monthly since March, various water quality parameters, and nutrient data, and also chlorophyll, which we've been sampling weekly since when? End of June. So the informal working group that we have here, and I think pretty much everybody from the working group is here in the room today. So we've got Bill and Tom, our lovely water samplers. They do the legwork for most of this. They're the ones putting the real work in. Charlie Capolino from the network, and Aaron Parazzini and Curtis Davis from Soil and Water, and then of course CWIO and FLI represented here. So yeah, thank you to all those folks who have been helping us out on this. There's our lovely picture of Bill putting a sample in a bottle over at Barrett Marine, one of our sites. So again, this is, you know, kind of our motivations here. And this is a picture of our research student who's been working on this over the summer, Jenna Smith, with well, one of our not so great ways to look at how the canal flows, but that's all part of the science, right? Oh, there we go. I didn't realize it was gonna do that. I guess it is. So these maps were provided to us by Soil and Water, so thank you. I think Curtis made these, so thanks, Curtis, for that. So you can see we're missing a pretty big chunk. If we cut the canal watershed out, that's a pretty big chunk of Seneca County. It's very comparable to the size of the Seneca Lake watershed in Seneca County, and is a little bit smaller than the Cuyahoga Lake watershed size. But you can see, you know, there's quite a few major streams that flow into the canal. And yeah, so it's a pretty big area that is.
I just the black line.
No, this, I don't, sorry, it doesn't show up well on this projector, but there's a blue line here. And that is the canal watershed. I don't know if it shows up any better on the second picture there. So it's about 46,700 acres. So these were our sampling sites for the nutrient and the chlorophyll data. So we had Barrett Marine, which is basically, you know, Seneca Lake water. It's right at the interface there where the Seneca Lake flows into the canal. Oak Island, which is a park in Waterloo. After Kending Creek enters, which is probably the largest stream in that watershed. The Route 414 bridge, which is right there, you know, where the burned area is in between Waterloo and Seneca Falls. It's right about there. There's a municipal dock in Seneca Falls, which is probably the nicest sampling site that we have. Johnson Street, which Bill likes to make the research students hike, you know, like 1.5 miles down through the woods to get to. And then Demont Road, which is just downstream of the Route 89 bridge. So, you know, where Route 89 here crosses. And it's also where Demont Creek, when it's flowing, will flow back and forth between the lake and the canal. So we tried to pick these some strategic locations. We tried to pick out, you know, most of where every major stream comes in, but also upstream and downstream of wastewater treatment plants, because there are 2 wastewater treatment plants, one for Waterloo and one for Seneca Falls. And so, am I talking about this part too? Okay, so this is the discharge graph. The USGS has a gauging station at the Route 89 bridge. And so this just shows our flow, and this, we can correlate these flows to our sampling dates. So unfortunately, we actually missed like the biggest flow event of the year, which happened, you know, right in this section here. But we've pretty well captured the curve, and you can see now, and Bill will attest to this if I ask him, but because Seneca Lake level has gotten down to its minimum level, they've pretty much stopped the hydroelectric generation. There are 2 hydroelectric plants on the canal. And so that's why we're basically seeing no flow for, well, most of August, really, because it's been so dry. So
So when that drops below 0, what is that?
So there's a couple of things, and we don't have a great answer to that, I think. It means that it is flowing backwards, essentially. So that's most likely just due to sloshing, you know, especially when they have things closed down. So like the gates that control the lake level for Cayuga Lake are closed at the moment. And you can see they were closed in May sometime. So, well, this says 89, so that probably doesn't show that, but they're closed at the moment. And then, of course, the hydro plants are not releasing water. They're not generating electricity. So the only water movement really is boat traffic through the locks when they're releasing water. So there is some just movement back and forth just from currents. But I think also this is probably skewed by boat traffic. You know, every time a boat drives by, of course, it's going to move back and forth. And so that's probably why you get those spikes that don't last very long, and then it comes back up to being pretty even. So I'm going to turn it over to Lisa now to explain the science side of things.
Actually, I want to go back to this, it's because. I think, so if for everyone who can't see in the back, the 0 level is here, right? So anything above this should be flowing towards the lake, and anything below that is kind of the sloshing that Isaac was talking about. And so, we originally started this project as an independent study for one of our students at Hobart and William-Smith colleges who wanted to assess water quality of streams that we just typically don't sample. And I think if we go back to why the New York State DEC samples streams, a lot of times it's because they're coming into the big lakes. Well, there's also a lot of streams that are flowing into important areas like the canal. So we wanted to make sure that we were paying due to maybe underrepresented streams and just provide some additional water quality to put the others into context. And so we actually started in March, which our first samples were collected when the snow was melting. And we didn't include that information in this presentation because we really wanted to talk more about base flow and kind of what we're seeing right now, kind of what is the average. But this is just the beginning of some of the work that we're doing, and Jenna's going to be, you know, carrying it on through another independent study as she's doing her senior integrative experience for environmental studies this fall. So this will be continued, and we're going to expand it a little bit from there. But again, for the back, this is now just looking at phosphorus, right? And these are the canal sites. We actually have 6 canal sites because when we did our first sampling, we left out Oak Island, which is in Waterloo, and we were urged by our, basically our management committee for this project to add Oak Island in. And so we now have 6, and we've been doing monthly sampling of nutrients. And so this is orthophosphate or soluble reactive phosphorus. The other one is total phosphorus. And I know you can't see that in the back, but the sites are going from west to east. And I want to say, if you kind of just look at the regular concentration, this is 5 and this is 10 for SRP or orthophosphate, very low. And we have not seen anything high throughout the weeks that we have sampled. The total phosphorus, this is 20. If you look at the CSLAP 5 site, which is Cayuga Lake in the north, the average total phosphorus concentrations are around 23.5. So the canal is right here with us. So we're not seeing any evidence of higher nutrients in the canal at this time. Snow melt, rain events might be a little different, but this base flow looks pretty good. Same theme continued for nitrogen. Again, I'm gonna spare you the numbers, but this is ammonium, what Stella was talking about earlier, very low relative to nitrate and total nitrogen. But our highest samples, and we did see some changes going from west to east in April with some pretty high nitrogen levels coming in the canal. And, you know, we can start to maybe look at some of those point sources that might be contributing. This is not at all meant to be viewed other than this is an assessment of chlorophyll. This is looking at the potential of harmful algal blooms that are in the canal. One of the things that we hear about from our campus is our rowing team actually practices in the canal pretty much all fall. And they, have reported some interesting water quality conditions out there. So we wanted to try to have a better understanding, whether there might be harmful algal blooms present in the canal, because it is kind of a, depending on the flow and the rain and everything, can be pretty stagnant in there. And so this is all the data that we have collected. It's weekly data starting from the last week of June up through the beginning of August. And it's chlorophyll A concentrations measured by a fluoroprobe. So a fluoroprobe will give you not only chlorophyll, but it will tell you the type of phytoplankton group that's contributing that chlorophyll. And so the one that we care about, and again, following on what Stella and Rick were just talking about, we care about these cyanobacteria. So this is the blue ones here. And the only thing that we've seen elevated so far, and it was approaching about 7.5 micrograms per liter of blue-green algae chlorophyll. A bloom, according to the state, is 25 micrograms per liter of blue-green algae chlorophyll. The highest level we've seen so far was actually at Barrett Marine, which was Seneca Lake water coming down. And so we haven't seen anything yet. However, we expect that we'll probably see something in the next 6 to 8 weeks and expect this to change, but it's nice to be able to track this over time. So then, how can we get about this question? How much canal water is flowing in, or does it even go into the lake? So the other thing that we have been monitoring when we've been doing these chlorophyll samples is specific conductance. So specific conductance is the ability of water to conduct electricity, right? So that is dependent on ions that are in the water. So things like sodium, chloride, calcium, magnesium, you can have nitrate, phosphate, anything that's a charged particle. And this is time on the x-axis here, starting at the end of June. This is the specific conductance levels in the water. This is the mean level of Cayuga Lake water. And that's about 400. Seneca Lake is about 635 on average in the canal. No surprise, right? We'd expect it to be right at Seneca Lake levels, especially when there's flow through the canal, because the water going through the canal, it's a complicated system. It seems simple, but we have renewable energy production, we have the canal corp, we have things discharging into the Seneca River to try to get out to Lake Ontario. But what we see as we go over time is that, and again, the back won't be able to see this, is that the sites closest to Seneca Lake actually stay pretty constant as far as what the specific conductance is. But as you go further downstream in the canal, you start to see an increase in the specific conductance. And we're starting to hit concentrations that are above Seneca Lake, and we're approaching like 800 microsiemens per centimeter, which is how this is measured. For our geology for the Seneca River Basin, those are not super high concentrations necessarily, but specific conductance is often used as a surrogate for pollution. So we thought that was interesting that, as you started approaching Cayuga Lake, that the specific conductance of the canal water is definitely getting higher. So then the question is, could we use specific conductance to actually trace the lake water, the canal water going into the lake? And so once again, Bill was kind enough to take out Jenna and Aiden in the boat and to do some specific conductance surveys. So if you're familiar with Cayuga Lake, this is the railroad bridge that comes in. Yeah, that cuts across the lake. So this is the northern part. And the canal is up here. So we started in the lake and then just went north towards the canal and measured specific conductance along that transect. And Jenna mapped this out using GIS to get it, to be similar distances apart. And as you can see, as you start And site one, which is in the lake. Which is, it's already elevated to what Cayuga Lake generally is for either site one, C-slab site one or C-slab site two. So we're already starting higher, but as you go further and further north, it gets higher as well. So there's clearly, and if you go into the canal, then it kind of levels out to that 800. So we're definitely seeing canal influence in this area. And so it's a very shallow area, but this worked a little better than the drifter that Isaac showed you the picture for earlier. So going back to when we looked at this, we're back now kind of in this August area where we were going over the 0 time. So the water is kind of sloshing back and forth in there. If you know that lake level management is a big challenge. We're always trying to discharge water, like when we know there's rain or snowmelt events coming, but it's a long road out to Lake Ontario, and it's a very slow journey. So one of the things that we're going to do moving forward is there's another gauge, if you will, or another place that is measuring discharge in the Seneca River, which is on the 5 and 20 bridge. So then we can also look at what's leaving the Seneca River or going towards the Seneca River, leaving the Seneca River heading towards Lake Ontario. This is our sampling period here. We know we got a ton of rain in May. And it's been pretty dry really since then. So, we're still completing the record is what I like to say. So as we move forward, we're going to continue this monthly sampling for nutrients through the end of the year. We're going to also continue this weekly sampling for chlorophyll as we move into half season. Anticipating that we might see some halves. I know they've been seen in the past, and we'll do total microcystids if it's warranted based on the blue green algae chlorophyll. We're going to continue to look at both of the gauges to try to understand what's happening, what data they're providing for us to better understand the flows. And then we're also looking at comparing nutrients in the physical water quality parameters to the CSLAP database for lake water quality over time. And last but not least, I want to thank Jenna. This is her research poster that she did from her work this summer. And so we'll be showing that at Parents Weekend shortly, but she'll be continuing this work, and we should have some other information to share in the future. And really, we wanted, I think, just to let you know that we're doing, especially in this northern part of the lake, we're trying to pay attention really to water quality writ large across the region. And we think that the Cayuga Seneca Canal is just one of those places that's a little bit understudied. And, it's been very interesting so far and what we've been able to learn from it. So thanks.
Questions?
So, does your research touch on issues of salinity between the two lakes?
That's what the specific conductance
Thanks.
is, exactly the survey. So yes. Because there's groundwater, right? There's other sources, there's other creeks coming in, other streams.
We have a salt line too.
That's, yes, but the lake itself should be reflective of what the specific conductance of the lake is pretty, maybe Liz, okay, you can help me with this, like from north to south, I don't think that there is that much. It's really just this northern part that's even a little bit higher. But Seneca and Cayuga are really high, right, because of the salt. Relative to the other finger mix. So
what piqued my interest a year ago was it's the first week of September with a huge public balloon in downtown Central Falls on Canal. And I believe at the time that was correlated to a pumping station failure at the corner of Kings and Ellery and 520. And so are you, I'm not familiar with this, but I understand that if there is a sewage overflow or a untreated water outflow from this sewage plant, that they have to basically report that. And are you tracking any of those and seeing if that correlates with any whether it's phosphorus levels or chlorophyll levels?
we would, yes, but I don't, Aaron, maybe you can help me out with this if there's have been any reports of, I don't think there have, that I've seen. Bill usually tells me too. Oh, that's-
Yeah, Bill's the one that pays attention to all this stuff for us.
But Aaron, do you have anything to say?
No.
I haven't heard, I mean, we've had a pretty dry summer.
So the overflows from sewage plants. And I believe pumping station, I think it's been pretty well managed.
From what I hear, yeah, that's, and I mean, as you know, it's hopefully gonna get upgraded here within the next year or two, so, yeah.
That's certainly another motivating part for doing this, right? Particularly when there's a lot of people that are around the water body, you wanna make sure public health is, being protected as much as we can. And,
Well, yeah, part of this too, to Charlie's point, was part of the impetus for this was that, Seneca Falls is doing all this downtown revitalization work and waterfront revitalization work, but the water doesn't look that good, so nobody's gonna wanna come and walk next to it if it smells bad and looks bad. So anything we can do to try and help with this, it's certainly Aaron is part of that too, since getting funding to do work in the canal watershed is difficult. There's no clean water plan associated with it. It's not considered part of the Cuba Lake watershed, so you don't have that backing to get grants and funding to do best management practices.
Yeah, from a soil and water perspective, this is really important specifically to Seneca County soil and water. Because when we apply for the local grants, it's competitive, generally competitive funding, and the canal, which basically makes up 1/3 of the watersheds in Seneca County, doesn't rank higher, not be able to met the projects that we want to, that we need to implement to meet water quality. And so if you look at those watershed boundaries, a lot of that canal watershed is made up of cash crop farms. Concentrated animal feeding operations are primarily focused in that canal watershed. And we're not able to get the funding to open those farmers to implement the projects that we need to install. So it really limits soil and water's ability to meet the water quality goals that we need to help protect not only the lakes, but the canal as well.
Yeah.
In the eyes of the state, what watershed is?
Senator. And kind of its own, right? I mean, the canal itself, but it is part of the larger Seneca River watershed. And what the state has said is basically all of this water coming down here just turns the corner and goes straight out down the river. That none of it comes back into the lake, and that's like everybody that you talk to, their opinion is, well, how can that be true? Especially when, the water control devices are closed, so all that water has to be coming back into the lake, at least at certain times of the year, right? It's not coming in all the time, and that's kind of where that USGS data comes in, the gauge stations, we can calculate, okay, if we have 400 cubic feet per second coming down the 89 bridge and 200 cubic feet per second going out at the 5 and 20 bridge, well, that 200 cubic feet per second has to be going somewhere, and it's probably in the building.
So when we apply for funding, we apply for the project and the data that we're sending away, it generally ranks really high because that's a water source for hundreds of thousands of people. But if we apply for funding in the canal, doesn't. And is an objective of this project to construct an appeal to the state to consider this part of the Cuba Lake watershed?
Yeah, or I mean, that, or if we can't get that, at least make this some type of waterway of importance, right? Because it's not like this doesn't just affects Cayuga Lake, it affects Cross Lake, which it flows directly through, and then Lake Ontario as well. And it, eventually ends up in Lake Ontario. So it's multiple water bodies that this portion impacts.
There's no water bodies that are able to explain it.
Right.
as part of these grant. The only current funding source that we can apply funds for practices is Finger Lakes, they can during the watershed protection alliance, it's called FOBA, and it's a the area for watershed.
But I think another part of this, right, is we really didn't know until we started doing this, and I think getting information about this is really important to try to help us scope the problem, right? We have how many things in our world need attention and things that need to be done, but we have to prioritize somehow. So this is at least providing us some additional information to help us make better decisions.
Yeah, certainly, there's been no, or very little
Very
water
personal
loss
stuff.
data. On the canal today.
And I think the waterfront revitalization program, I think that is a really excellent point. I mean, Charlie kept when we would have our meetings, he was reminding us, you know, that there was going to be a symphony orchestra on the canal during July 4th holiday. And, you know, and tourism is a huge driver for this region in general. And we know it's tiger water quality. So we want to understand, you know, these connections between some of what's happening on the land along with water quality and how it impacts people.
Yeah, I need to secure the state, this water area, then you have.
Not that I know of, but Barbie, you might know, you pay attention to that stuff too.
Yeah, not that I know of, but right, it would be a change, I can't remember now, if it's in environmental conservation law. Where the watersheds are listed out, that might be. What? No, it's shame. I don't think where the watersheds are listed out and then we'll get a clean line. So, and that would be what we would need to have changed at the state level. It is designating what the watershed is and then, so it's gonna. Be on city years since I looked into this, that might be part of the, like, what's the next step of like, what do we do to get this incorporated? People like watershed.
I don't know.
I don't know, yeah, that's, yeah, I don't recall.
Yeah, so. Taking out these. You guys said the question. Yeah. That's a little bit thing to think about, plus. When I'm thinking the board of supervisors, a lot of sense in the resolution, it says, okay, we need to look at this. We've learned now, the research that demonstrates that this is more important than what. When we look at it, we really look at that, right? I mean, I made this practice. You include parts of the depot and you can freeze the land. People. Lisa could talk all, you could talk all day about that. Yeah. Water. Well, we have an impact on water quality. Clearly is.
So that was kind of the impetus for the project that Stu did last year, and we have sampled just Black Brook, Gem Creek, Black Brook in several locations, Collar Road, we've also done Sylvan Creek, Suffering Brook. Others have done Kennedy, we're gonna add it on, and that's part of the stuff that Jenna's gonna follow up on. I mean, I think a lot of times, right, there's not a lot of flow in the streams, but there, if you look at how the water is moving, we know which direction it's moving in. And so, I think we're just trying to get some more information about what we're finding out.
So also, is there a way of using, I would like my masters in solutions. Is there a way to trace back using isotopes or something and say, okay, my fields of the water suffer? I've seen it take TV set a mile. Is there a way to trace back that water is, where did it goes the 1953?
Yes.
Yeah, is it just a political thing or not believing that?
Yes.
Know the answer?
But I think it's mostly funding for research projects that would be of the right size, scoped of the right size to be able to answer those questions. You would definitely be able to come up with something using nitrogen isotopes to look at that. There's a lot of effects on nitrogen isotopes, nitrogen cycling affects them. So you might want to think of even doing something like, combining a carbon isotope, something that doesn't change as much when,
That's really what a lot of nitrogen. That's a little lot. But just getting like, well.
yeah, good application.
Goes back here, so about.
You can also do ratios of different elements to each other and see when they're present together and look at events, and so. In the spring samplings that we did, we sent a lot of trace metal samples to Dartmouth, we had them in the lab for doing trace elements and IEHS. But they have instrumentation to do trace metal analysis, but it is one of those questions, and so saying it's like. A lot of the basic research or applied research, we just don't. We know what to do, but there's really no funding on what to say to move for independent projects like this, unless the DEC wants them done. And I don't know who's here from the DEC, I will deny saying that. But it is a bit of a challenge. So this is where some of this pilot data really helps us take the next step and trying to better understand what's happening.
When we pointed at state is putting a lot of money into canal frontage in terms of basically making that a dealing place to go and bring tourists and such. And look at downtown outside of Falls, for example, they were put in several $1 million for improvements. And they just put a kayak launch in downtown Central Falls, and it seems like it's a pretty reasonable argument to go to say, look, you're putting all this money into the infrastructure around the canal. Maybe you take a percentage of that and put it into improving the water quality. Who wants to kayak in a canal? I think it's better this year than last year, and instance last year, but it was a pretty bad year.
Yeah, certainly last year was just worse. We saw that with the lakes too, right? I think we're not having that's quite as bad a year past as we had this year. Listen,
Political standard, like why put most money in that? Because it's kind of seems like it's a technical step earlier in terms of that watershed and not being part of the assessment. Said of importance can be drinking water, but can also be tourism economy that you're investing in that, investing in quality of water. I think that's true with the terminal. We look at market gas and X and sales tax. We lose that, we are screwed. It's just, I'm sorry, I'm wrong, but that's the reality. Yeah, they're great points. Great.
If people have questions for Stella and Rick and their research, I don't know. I felt like we left a couple hanging there. Are there other questions that people have? Oh man, really? You just ran out of